Thanks, Karen. Good afternoon. It's a pleasure to have this opportunity to talk about some of the priorities in the natural resource economics area, with a particular focus of my talk today is going to be on water, land, ecosystems, and environmental policy. So thank you all for joining in to this webinar. Part of the, my talk is really going to draw upon some of the recent discussions and workshops that have been held, in particular focusing on the importance of the food, energy, water nexus, as well as sort of this growing interest in conservation and behavioral economics. And so, and again, this is not to discount the importance of other areas that we should be working on. I'm just highlighting a few that have sort of surfaced, given my interest, as well as some of the recent calls for proposals from NSF, NEFA, and other agencies that have been emphasizing, trying to integrate issues around land, water, ecosystems. And so, in particular, I think from this is particularly relevant for agricultural economists because some of the grand societal challenges that we're facing relate to issues that we deal with, that we study intensively, and so are really in our area, in our wheelhouse. And in particular, these relate to the fact that there's a lot of concern about food security, about trying to feed 9 billion people by mid-century. There's increasing demand for energy, and with the concerns about mitigating climate change, this has led to interest in bioenergy as a way to reduce dependence on fossil fuels. And so all of that sort of causing increased demand for land to meet demands for food and energy, as well as water, irrigation water. And this is all happening with the growing threat of climate change, which has a potential to significantly reduce crop yields, as well as impact the suitability of cropland for crop production. And at the same time is accompanied by concerns about the environmental footprint of agriculture, and the water quality implications of agriculture production are one of the major areas of concern. The hypoxia zone shown on the right has been growing, and to a large extent is caused by agricultural and livestock production activities that are particularly challenging to regulate and control. And again, for reasons well known to agricultural economists, concerns, this is related to the fact that as knowing point source pollution, this is very difficult to observe, measure, regulate, and hold polluters accountable for. Additionally, the impacts of agriculture are multidimensional. So agricultural activity affects not only water and water quality, but also greenhouse gas emissions and biodiversity. And so, so the challenge is to take a holistic view of the impacts of agriculture on the environment and identify strategies to address those. So looking at these interactions among, between food production and the environment is not new for what we do. I think what is new is the approach perhaps that we have been taking. There's been a lot of work looking at the impacts of water and energy as inputs into food production and how to increase productivity, and also of looking at the outcomes of agriculture production, in particular looking at, say, water quality and greenhouse gas emissions. More recently, in the last, within the last decade, there's been growing, production of biofuels mainly from corn ethanol, and that's created this competition, or between land for food and bioenergy production, and led to a lot of research looking at food versus fuel, and the the inputs going into bioenergy, as well as the potential for bioenergy to mitigate greenhouse gas emissions and its impact on water quality. But most of this research on bioenergy in particular takes the food side of the analysis as pretty much given, and then looks at the impact of imposing additional demands of bioenergy on an existing system and the competition and conflicts that it poses. I think what I'm sort of suggesting here is moving more towards a holistic view of the entire system, recognizing that, and then looking at ways that we can optimize land allocation so that there's a two-way interaction between food and energy production, and ways to look at not only the traditional ways or the conventional ways of producing bioenergy from food crops, but also the new and advanced methods that are being studied for biofuels from perennial energy crops, which would allow for a much more diversified agricultural system that not only produces food but also energy in a way that can lead to improved ecosystem services, and recognizing the role of the feedback, the role of climate in governing this production system, and the feedback effects from the environment to our human actions that then go into adapting to climate change, looking at mitigation strategies, and so on. So we've so I think as we've been looking at various pieces of this whole picture in depth, and what I think that the challenge is to take a much more holistic and an integrated view of the entire system. And of course, this is not easy. This is a major science challenge, which is why NSF has spent $50 million or under their recent call for proposals for integrated food, energy, water systems, and proposed to spend another $75 million in the future to promote research that takes this holistic view of food, energy, and the food, energy, and water nexus. What this sort of calls for is taking a systems view to sustainable food and energy production that recognizes the need for a much more interdisciplinary approach that can, links the economic models and the economic decision-making framework with biophysical models that can tell us about the outcomes of those economic decisions, and then that can feed into looking at what the outcomes are in terms of the market outcomes as well as the non-market outcomes, what the values of those goods and services are, and how those should impact human decisions, so that we, and again, economists are, a lot of our work has been at the front end and at the front and the tail end of that, both in terms of being able to model economic decision making as well as the outcomes of that, and how do we value those not only the market but also the non-market goods, and together in conjunction with biophysical models that can help to design an optimal land use and an agricultural system, and guide the policies that are needed in order to move us away from business as usual to a more to a preferred outcome. And so what we're talking about here really are new equilibria that looking out into the future. What are these new equilibria that we would like to achieve that can provide us not only food and feed, but also environmental services and bioenergy. And studying this requires, of course, taking a dynamic view of the system, recognizing the potential for technological change, and also recognizing that even when it comes to environmental outcomes, it doesn't, trying to address one environmental outcome at a time, which is typically what we tend to do, is to look at the impacts on say greenhouse gas emissions or on water quality, but recognizing that that these outcomes themselves offer some synergies and trade-offs that we need to incorporate when we are trying to design a sustainable food and energy production system. And so, studying this food, energy, environment trilemma essentially requires understanding what are the implications of moving towards more sustainable intensification. So, the land is ultimately a fixed resource. As we, increasing productivity and increasing production in a way while achieving conservation requires more intensification, but in a sustainable way, and that requires conservation practices that impose have implications for private costs and risk as well as societal risks, and better understanding what these social and private risks and benefits are with these practices is important in order to understand what the barriers and the incentives for moving towards such a system are. And so this is sort of on the supply side, but then on the demand side, we also are observing this growing interest in local and organic foods, and understanding what the implications of that are going to be, given a system where we are also at the same time trying to increase food security, increase food production, double food production, and how to achieve that, where demand, that synergy between the demand side and the supply side is important. So looking at the implications of this change in demand for food security for the environment, what are really the benefits of local foods, and then what are the implications for both consumers and producers of this shift in demand. A third issue is the issue of better management of land, and so to the extent that there is fallow and marginal land, what are the uses that it should be put to? One option would be to just extensify crop production, but possibly have negative impacts on the environment. The other extreme would be to retire that land from crop production, which is of course very costly to do. But there could be other ways to have more diversified production systems that can lead to some complementarities between meeting our needs for example, bioenergy from perennial grasses, while also achieving desired environmental outcomes. And so managing these complementarities and trade-offs between alternative uses of the land and the environmental outcomes, I think, is going to be an issue of increasing interest, and yet at the same time represents a major science challenge. Another area that I think is ripe for further study is the need to sort of go beyond the rational profit-maximizing view of the farmer, and to study the effect of behavioral and other factors that can affect the extent to which conservation practices are adopted, the kind of incentives that are needed to encourage and accelerate adoption. And those include things like the risk perceptions of the farmers and their attitudes, and which can limit adoption, as well as the time preferences. Many of these types of practices involve upfront costs. Their returns and outcomes are often uncertain, and so understanding how time preferences play into that, into the reluctance perhaps to adopt technologies that otherwise might look profitable is important. And so there are a number of best management practices that appear to be win-win solutions, but if one takes into account risk and time preferences, then it becomes more clearer why we see limited adoption of these types of conservation practices. We also know from some of our research that social networks and peer effects are important drivers and important sources of information for adoption, and so better understanding of how these can be leveraged in order to induce more adoption is an area for research. Behavioral economics is increasingly showing the role of inattention, surge costs, the benefits of nudges in leading to adoption of technologies that might in some cases even be economically viable but are not adopted. And so using experimental behavioral economic methods to design incentives that increase participation, cost effectiveness of conservation programs is, I think, is important and deserves greater attention. We can see from the right that under the recent Farm Bill, that funding for federal conservation programs has been declining. And so the extent to which one can rely upon the government to provide financial incentives to achieve all our environmental outcomes is questionable. And it's important to design cost-effective programs while, but at the same time also recognize that there is, market-driven incentives and response by major agribusinesses in response to those to try to provide more sustainably produced food. And a number of food companies are committing to sustainability, reducing waste and pollution and so on. The extent to which these can be relied upon to achieve, again, desired societal objectives is to be investigated. There's been, research on this. There's room for more and for adapting our research in order to continue to investigate the potential for these private sector voluntary initiatives. On the policy design side, which again, our profession studies intensively and has the expertise to do so, we've done a lot of work looking at the environmental implications of agricultural production and recognizing the non-point source nature of this agricultural pollution and, study the cost effectiveness of a range of first and second best policies, including green payments, in order to mitigate the adverse impacts. We've also studied the effects of asymmetric information, which is inherent in the whole production process and its linkage to environmental outcomes. But most of our research tends to focus on a single agricultural pollution at a time. Of course, we know that when there are multiple pollution problems, you need as many instruments as there are pollution problems to deal with. But of course, that isn't the case where the pollution problems are independent of each other. And I think there's increasing interest in looking at pollution problems that are jointly determined, where you might have co-benefits. So mitigating water quality effects could also lead to increased greenhouse gas mitigation, for example. Or in some cases, it could be the other way around. As we try to mitigate greenhouse gas emissions, for example, with corn ethanol, we may worsen the water quality problem. So trying to understand the practices and the policies that can lead to these complementary and conflicting effects is important in order to not worsen one problem as we try to solve another. And so policies that address the jointness in these environmental effects is important. And it's important in order to consider how to design such policies, because if we treat each of these outcomes in isolation and seek to develop policies that would penalize or reward farmers for addressing them, that could lead to sort of stacking of payments and this double dipping problem where it would involve paying farmers multiple times for the same activity because it leads to multiple outcomes. But on the other hand, designing, in order to avoid that, requires understanding the additional effects of each policy on particular environmental outcomes, and that can be used then to design more cost-effective policies. But of course, that's challenging to do because the outcomes are not easily measurable, and so determining additionality is not a trivial issue. The third alternative is to think about bundling payments and rewarding farmers on, for example, a per acre basis for multiple services that come out of their switching to a conservation practice. But again, determining what those payments should be and how they might differ spatially is a key issue. in addition to sort of thinking about how do we design new policy, there's a question of if you're looking at existing policies, and many of these policies may be not necessarily targeted to environmental outcomes, but have spillover effects on the environment. And so a number of, crop insurance, commodity policies, for example, analyzing their effects on land use and social welfare and the environment is important. And similarly, looking at the implications of multiple policies that are often implemented simultaneously to achieve very similar objectives. These policies can also conflict with each other and have unintended consequences that can raise the overall cost of achieving an objective. And so, for example, just to induce a switch to renewable energy, we've got the renewable fuel standard, the renewable portfolio standard, a new and emerging clean power plan, all of which would, when implemented simultaneously, would create incentives for bioenergy, for example, and that could lead to greater competition for the same resources and the same feedstocks, and raise the cost of achieving all of these policies, as opposed to, say, one that were to be more streamlined and try to get to the same objective, but in a more targeted and cost-effective way. Now, so turning a little bit to sort of on the technology side, there's, of course, we know there's emerging capabilities to gather big data and to use big data to enable improved farm management. Currently, of course, our agronomic and crop management information is aggregated at the field scale. A lot of our analysis are often based on things that are aggregated to a county scale, and so this would lead to, given that there's a lot of heterogeneity in how spatial heterogeneity and soil quality and climatic conditions and so on, aggregated decision making based on aggregated data is likely to lead to inaccurate assessments of production functions, environmental processes, and outcomes. And so there's increasing capability of using information on a very fine spatial scale on site-specific soil characteristics, weather, and then combining that with technology that allows variable rate application of inputs that respond to those differences in site-specific characteristics, using mobile technologies to have real-time information is to inform decision-making, and better data management software can enable more site-specific farm management. And this has the potential to increase yields, increase input use efficiency, decrease input waste and input cost, decrease runoff, and potentially lead to these win-win outcomes. But of course, it's important to understand the costs at which it could do that, the incentives and the barriers to doing it. Currently, of course, most of this big data service is being provided by big businesses, and there's a number of examples of that listed here, of companies like Monsanto, DuPont, John Deere, Pioneer, etc., providing services that allow more site-specific variable rate applications and management of the field. Of course, this calls for an area where agriculture economists can contribute is in interpreting data, analyzing its implications, deriving decision rules, looking at the costs and benefits, not only from a private perspective but also from a social perspective. So big data can actually inform research, improve our understanding of the site-specific yield and environmental response functions. It can also lead to more informed science-based policy, and potentially it can enable spatially differentiated policies that can be targeted now to be much more effective, and perhaps move us away from the current set of policies where the victims sort of pay the polluters to a more of a polluter pay policy, by converting non-point pollution to a point source pollution, by enabling us to learn exactly which fields, which practices, which areas of the field are in fact contributing the most to environmental degradation. The challenge with this is that the data is currently not available publicly. There's a lot of confidentiality concerns, and so designing systems that would allow for the provision of this data either voluntarily or mandatorily to government, to researchers, while preserving privacy and confidentiality is an area for greater investigation and research. It wouldn't be the first time that such a system for data confidentiality and privacy would be designed. We have, the National Agricultural Statistics Service that has the arms data that is again confidential, where the confidentiality is preserved, but it's made available to researchers. Similarly, the Census of Manufacturers data. And so designing similar systems where big data could be made available for research purposes would enable more use of this data for research and policy making. And so this really calls for greater public-private partnerships, streamlining this data collection process, building a secure data system, and then utilizing the data to study how it can lead to private and societal benefits. The last topic that I want to touch on very briefly is looking at climate change. And of course, there is increasing evidence, concern of climate change, and a lot of research looking at its effects on agriculture in particular. A lot of this research has tended to use sort of reduced form, production function, and Ricardian approaches to understanding the impacts of climate change on crop yields, as well as on farmland values and so on. And I think we need to sort of go beyond that to take more structural approaches, because the reduced form approaches, while they're great at providing a measure of the impacts of climate, temperature and climate variables, but they do so in more in a sort of a partial equilibrium setting. And one of the things they omit are the possible price feedback effects of changes in global production levels on prices, and therefore on adaptation and responses by farmers to that. And so they're based on in some ways on this, at least the reduced form production function approaches are based on this sort of dumb farmer view, where they assume that there's no response from the farmer as production continues to decline in response, or yields continue to decline in response to climate change. Much of this research has sort of focused on examining the effects of mean temperature and not of extreme events and variability, which we know are key signature consequences of climate change that should be examined. And then looking at, in particular with the Ricardian approaches, they do not consider the time path of adjustment. So looking at two equilibria, but not the time path of adjustment and the consequences of that in terms of the distributional impacts on consumers and producers as we adjust to the new equilibrium. So in addition to that, in addition to these reduced form approaches, it's important to have a greater understanding of the causal mechanisms by which climate change is likely to affect a range of outcomes of interest to us, including yield and agricultural profits, but then also the mix of crops, planting dates and its consequences for the mix of crops that we can grow, pests and diseases and their economic implications. Human migration is a key key outcome that could be affected by climate change. There's already anecdotal evidence that that's happening. Similarly, effects of pests and diseases on human health and effects of even temperature directly on human health is an area of emerging interest. Forest growth and fires, biodiversity are some of the other outcomes of climate change, and understanding what the economic consequences of this would be and valuing it, I think could enable more, or could enable greater urgency of policies to address these, and as well as the design of those policies. And then understanding what, not just the effects of means, but then also these nonlinearities and the threshold effects that can happen, and what their consequences might be, which is important. I think there's obviously great room for greater work on adaptation to climate change and what some of the incentives and the barriers to that are. What are the triggers to adaptation? In particular, are those extreme events, or would gradual change trigger it? Do short-term fluctuations in climate lead to adaptation behavior, or do we need to see permanent long-term effects before farmers are induced to adopt adaptation practices? Understanding heterogeneity in adaptation and why we may not see it uniformly across the landscape because of just behavioral responses may be very different across individuals, and there are other barriers such as high discount rates, credit constraints that can limit incentives to undertake adaptation activities that involve high upfront costs with uncertain and long-term benefits. And then additionally, the unintended consequences of government policies. And so looking, for example, there's work now looking at the effects of crop insurance and how that might reduce incentives for adaptation by taking away some of the risks from continuing the current set of practices. Similarly, crop subsidies could also reduce incentives for adaptation. So trying to see what are the unintended consequences of existing policies and how we can create better incentives for undertaking adaptation. So, so in some, highlighted 4 major areas that I think are of emerging importance, and I think and areas that we are already well placed to, as a profession, to investigate and contribute our expertise to. The first of these is sustainable strategies for land use management to meet growing demands for food, energy, and environmental quality. The second is looking at ways to induce and accelerate conservation behavior so that there is more sustainable intensification, and understanding what the public and the private sector role in providing incentives for this might be. The third is understanding the role for technology-enabled farming and its private and societal benefits, and how to enable the use of big data for research and policy. And the last is greater study of the impact of climate change, as well as the potential for adaptation, strategies to undertake adaptation, and to mitigate the adverse impact of climate change, and and understanding its economic and distributional implications. So let me stop with that and be happy to take some questions.
Great, thank you, Madhu. There are so many different issues